Thank you all for tuning in and making it to part 2 of this textbook. Chapter 7 focuses on how transistors, specifically MOSFETs and BJTs, are used as amplifiers. The chapter explains their operation, design considerations, and how they amplify small signals, making them vital for both analog and digital electronics. Basic principles of amplifier operation. Voltage-controlled current sources. Transistors operate by controlling current flow with voltage, enabling amplification. Nonlinear behavior. Transistors naturally exhibit nonlinear control, but by properly biasing the circuit, they can amplify signals linearly. Why it's important. Amplifiers are the backbone of signal processing in technologies like communication systems and audio equipment. Voltage amplifiers. Transistors act as transconductance amplifiers, converting input voltage into output current, which is then converted back into voltage for amplification. Examples include simple amplifiers using either MOSFETs or BJTs. Why it's important? Voltage amplifiers are fundamental for boosting weak signals in devices like microphones and audio systems. Voltage transfer characteristic, VTC. The VTC graph shows how input voltage affects output voltage, with linear amplification occurring in specific regions. Proper biasing ensures the circuit operates in the linear range, avoiding distortion. Real-life example. VTC is crucial for designing circuits that amplify voice signals in telecommunication systems without introducing noise or distortion. Small signal models. Small signal models simplify how transistors behave for small variations in input signals, making it easier to design and analyze circuits. Key parameters, like transconductance and output resistance, define the amplifier's behavior in this model. Relevance. These models are widely used in designing RF amplifiers for communication systems, where precision and efficiency are critical. Voltage gain. Voltage gain describes how much an amplifier boosts an input signal. While MOSFET amplifiers are common in digital systems, BJTs often provide higher gain, making them preferred for analog designs. Example: high-gain amplifiers are essential in medical devices like ECG machines, which need to magnify tiny electrical signals from the heart. Graphical analysis. Load line analysis, a method used to visualize the operating point of a transistor in a circuit. Switching behavior. Transistors can also be used as digital switches, transitioning between on and off states. Relevance. These concepts are vital for designing efficient switches in digital systems, such as CMOS, logic gates. Design considerations. Amplifier design involves balancing gain, signal swing, and linearity. Proper biasing ensures the amplifier can handle a range of input signals without distortion. Real-life example. Audio amplifiers are carefully designed to handle soft and loud sounds without clipping or distortion, ensuring high-quality sound reproduction. Practical circuits. Discrete circuits. These use individual components like resistors and capacitors along with transistors, often seen in custom audio equipment. Integrated circuits, ICs. These predominantly use MOSFETs and are the foundation of modern electronics like smartphones and computers. Why it's important. Discrete circuits are ideal for specialized designs, while ICs dominate consumer electronics for their compactness and efficiency. Comparisons between MOSFETs and BJTs. MOSFETs, higher input impedance, lower power consumption, and better for digital circuits. BJTs, higher gain and better performance in high current analog applications. Example: Hybrid BICMOS technology combines both for high-speed, low-power designs used in processors and communication systems. Noise and amplifiers. MOSFETs tend to produce less noise than BJTs, making them ideal for sensitive applications like audio processing or instrumentation. Types of noise include thermal noise and flicker noise, both of which can degrade circuit performance. Real-life example. Noise reduction is crucial in hearing aids, where even small amounts of interference can impact clarity. Why this chapter matters. This chapter equips readers with the foundational knowledge needed to design amplifiers, highlighting their significance in both everyday electronics and advanced technologies. Thank you for tuning in. Join me next time as we dive into the building blocks of IC amplifiers in Chapter 8.